Okay, in section 3, I'm going to go through 3 examples, go through the details of actually finding the eigenvalues and eigenvectors and getting the general solution. And one of the examples, all 3 of them, the origin is equilibrium point. The origin will always be an equilibrium point for the systems that we're looking at in this chapter, y prime equals ay, where a is a matrix. And usually it'll be the only one unless the matrix is singular, which it won't be in these 3 examples. So in these 3 examples, the only equilibrium point is 0, 0, but we want to see what happens near the equilibrium point. Does it suck them in, blow them out, or what? First example, the matrix is this. So we find the eigenvalues, we subtract lambda from the diagonal, take the determinant 5 minus lambda times 4 minus lambda minus 2 times 1, simplify that, and we can factor it. If you can't factor it, then if you get irrational roots, that's okay. It makes the arithmetic more complicated, but it's really nothing different if the roots turn out to be 2 plus or minus the square root of 3, say. If they turn out to be complex, that is, if the discriminant is negative, then you have complex eigenvalues, then that's a whole different ballgame. We'll talk about that in section 4. If you have a 0 discriminant, that means you have 2 real roots. That's a different ballgame too. In this section, we'll always have 2 distinct real roots, and my 3 examples, they'll be nice integers, but they don't have to be integers or even rational numbers. But anyway, so the eigenvalues, this does factor. Didn't need to use a quadratic equation. The eigenvalues are 3 and 6. So what are the eigenvectors for each? Well, one at a time. Lambda equals 3. To find the eigenvector, that means that's the vector xy such that this matrix times xy is equal to 0, 0. So we just solve, subtract 3, put in lambda equal 3, subtract 3 from the diagonal, and we get 2, 2, 1, 1. Notice that this matrix is obviously singular. That is, the second row is just a multiple of the first. That will always happen. If it doesn't happen, something's wrong, because the lambdas, the eigenvalues, are chosen so that this matrix is singular. So the second row should just be a multiple of the first, which means you can ignore the second row. Well, if you do Gauss elimination, take a multiple of this and add to that, you'll end up with 0 rows, and of course 0 here. So basically you can ignore one of the rows if they're essentially the same. I mean, this says 2x plus 2y equals 0. That's the same as x plus y equals 0. So 2x plus 2y equals 0, or x plus y equals 0 means x is minus y, and you can take any value for y you want. Might as well take 1, and the x will be minus 1. And you could take y to be 10 and x would be minus 10. That's just as good. It doesn't matter because you're going to be multiplying this by an arbitrary constant anyway. So any non-zero solution to this is eigenvector. And then the other eigenvalue is 6. We do the same thing for it. Subtract 6 from the diagonal. And now we end up with, again, the second row is just a multiple of the first, so ignore it. And we've got x, or ignore the first one. They're the same. One's just a multiple of the second equation. So minus x plus 2y is 0, or x equals 2y, so you can take y equals 1 and x equals 2. And so we've got the 2 eigenvalues, 3, and minus 1, 1 is the eigenvector, 6, and 2, 1. So you put them together, and here's the general solution. One solution is e to the first eigenvalue times first eigenvector. Other solution is e to the second eigenvalue times second eigenvector. And the general solution is linear combination of those. Don't have any initial conditions, so we don't. We're just going to leave it as a general solution. And we're going to look at this for various starting points. But notice that 0, 0 is an equilibrium point, and it's obviously a source because both eigenvalues are positive, which means that as t goes to infinity, this constant gets large and this one gets large, so the sum goes off to infinity. So if you start exactly at 0, a and b will be 0 and you'll stay there, but if you start a little bit away, you'll get blown away. So if both eigenvalues are positive, that means it must be a source. And now let's look at the phase plane. See, this is an autonomous, in this chapter there are autonomous problems because there's no t on the right hand side, and so we can draw the phase plane at each point xy. You can draw x prime, y prime, and that says if you're ever in that point, go this direction. So draw a little arrow. So let's look at the eTools phase plane. Okay, the matrix A was 5, 2, 1, 4. So here's your system, and well, you can just see by looking at the arrows that at the source, if you start exactly at 0, 0, it will stay there, but if you start just a little bit any direction, it gets blown away. As predicted, since both eigenvalues are positive. Okay, there's another example. This is the matrix. Subtract lambda from the diagonal, take the determinant, and you get factors as lambda plus 2 times lambda plus 5. So the eigenvalues are minus 2 and minus 5. And by the way, you already know that it's going to be a sinc because both eigenvalues are negative. It doesn't really matter what the eigenvectors are. You're going to have an e to the minus 2t and an e to the minus 5t multiplying the eigenvectors. They're both going to go to 0 with time. So we find the eigenvectors anyway, the same way as before. For example, minus 2 has eigenvector minus 1, 1, or any multiple thereof. Minus 5 has eigenvector of 2, 1. So there's the general solution. Minus 2 has this eigenvector, minus 5 has this eigenvector. And you can see that no matter what, the initial condition determines what A and B are, but no matter what initial condition, what A and B are, both of the amplitudes are going to 0, so you start away from the origin, it's going to get sucked into it, so this should be a sinc. And let's verify that. Okay, this problem, the matrix was minus 4, minus 2, minus 1, minus 3, and you can see from the field it's already a sinc. If you start at 0, 0, of course you stay there. Any equilibrium point, if you start there, you stay there. That's the definition of equilibrium point. But what we're interested in is what happens if you start close to it. Or, as a matter of fact, the 0, 0 is always an equilibrium point for these problems, and it really doesn't matter if it's a sinc. You can start as far away as you want, and it'll get sucked in. If it's a source, you can start as far away as you want, and you'll get blown away. Whereas more general problems like the predator-prey, source or sinc means assuming you start close to the equilibrium point. Well, anyway, you can see that it's getting sucked in no matter where you start, which is what we'd expect, just from the fact that both eigenvalues are negative. Okay, the last eigenvalue matrix is this. And again, subtract lambda from the diagonal, take the determinant, set it equals 0, and it factors. It won't always factor, of course, and eigenvalues may be complex, in which case we have no idea what to do yet. So the eigenvalues are minus 3 and 2. So notice now 1 is negative, 1 is positive. That's a saddle point, regardless of what you don't need to know the eigenvectors to know that it's a saddle point. That means in some directions it's going to get sucked in, some directions it's going to get blown out. So, skip the details here, but one of the eigenvalues is minus 3, and that's the corresponding eigenvector. Other eigenvalue is 2, that's the corresponding eigenvector. So A and B depend on the initial conditions, but you can see that this term is going to be going to 0, and this one's going to be going to infinity. So in general, it's called a saddle point because it's sort of half source, half sinc, except it's a whole lot more source than it is sinc. Because unless B happens to be 0, in other words, unless you start with a multiple of this single vector here, if this goes to 0 and this goes to infinity, what's 0 plus infinity? It's infinity. So the positive one wins unless its coefficient is exactly 0. So a saddle technically is part source, part sinc, but it's mostly source. So here's the last problem. The matrix was 0, 1, 6, minus 1. And you start most anywhere, you'll get blown away. If you start exactly at, let's see, 1 minus 3 or any multiple of that, this is what the eigenvector corresponding to the negative eigenvalue was 1 minus 3. And let's see what happens if we start at 1 minus 3 or any multiple of that. Then 1 minus 3 is here. It gets sucked into the origin until it gets real close, then it gets blown away. It just because of round off error. In other words, it should go to the origin in theory and should stay there, but it's tiny bit of round off error makes it go unstable. So this is a lot more source than sink. If you start most anywhere else, you get blown away without even going toward the origin. So only if you start exactly on this line will you not get blown away, and even then you still get blown away because of round off error. So with real eigenvalues, you can have, if they're both positive, you have a source. If they're both negative, you have a sink. If one's positive, one's negative, you've got saddle point, which is more of a source than a sink. With complex eigenvalues that we'll study in the next section, more interesting things can happen. And just to give you a preview, here's a case where the matrix is minus 1, minus 2, 20, 0. And we start most anywhere here, and it spirals in to the origin is an equilibrium point for all of these problems. This one is called a spiral sink because it spirals forever as it goes. It gets sucked in. It's a sink, but it spirals. Now, if we make one little change here, now you start close to the origin and it spirals out. So this is a spiral source. And finally, with this matrix, 0, 1, minus 8, 0, look what happens. It doesn't spiral in or spiral out, it just spirals forever. We'll figure out how to predict this kind of behavior in the next section by looking at the eigenvalues again, which are going to be complex.